For years, Washington's brilliant strategy relied on a simple premise: deny China the Dutch Extreme Ultraviolet lithography toys, and they'd be stuck in the semiconductor stone age forever. But rather awkwardly for American politicians, Huawei didn't just sit around crying over missing equipment. They fundamentally rewrote the oldest rule in the Silicon playbook with absolute sheer audacity. The sacred doctrine was Moore's law, demanding we endlessly shrink tiny transistors on a completely flat surface, which inevitably hits a rather nasty physics wall of extreme electrical resistance. Instead of desperately squeezing microscopic parts horizontally, Huawei essentially asked, why not just fold the bloody thing and stack those logic circuits vertically like a high-tech microscopic skyscraper? This cheeky revelation in Shanghai introduced something called the Dow scaling law, prioritizing the time signals travel instead of obsessing over physical transistor sizes like the rest of us. You see, in conventional modern chips, more than 80% of your precious energy is utterly wasted just dragging data across incredibly tiny, highly resistant flat metal highways. So, Huawei simply slashed the commute. By folding logic layers directly on top of each other, electrical signals travel micrometers vertically instead of agonizing millimeters across a flat plane. This requires an astonishingly aggressive hybrid bonding pitch, connecting the stacked silicon layers with millions of microscopic vertical elevators to absolutely avoid a horrific electronic data traffic jam. Frankly, achieving this precision without the world's fanciest Dutch machinery is a bit like performing flawless brain surgery using a rusty spoon, yet Huawei claims near-perfect manufacturing yields. The results are delightfully terrifying for Western competitors, delivering a 53% jump in transistor density without needing to endlessly beg Washington for export licenses or fancy lithography machines. They squeezed roughly 238 million transistors into a single square millimeter, effectively matching the capabilities of the most advanced tech currently churned out by Taiwanese manufacturing giants. What makes this terribly embarrassing for the original chokehold strategy is that Huawei managed this incredible density using much older manufacturing nodes from 4 generations ago, defying all expectations. Instead of printing smaller features with inaccessible extreme ultraviolet light, they masterfully engineered multiple patterning on legacy machines, stretching deep ultraviolet capabilities far beyond what its creators ever intended. And the sheer performance metrics are frankly staggering. This folded logic architecture purportedly hits clock speeds of 3.1 GHz, a milestone practically everyone assumed was entirely unreachable. By drastically shortening those internal transmission pathways, Huawei naturally reduced clock skew and eliminated half of the necessary signal buffers, rendering the entire silicon package vastly more power efficient. This efficiency translates to a massive 40% performance gain for artificial intelligence infrastructure, easily sidestepping the severe hardware export limitations placed on training enormous models by the West. However, the real punchline is that Huawei completely bypassed the traditional geometric scaling roadmap, effectively proving there are alternative routes to achieving next-generation processing power without shrinking the components. By completely changing the underlying metric from physical size to signal timing, they rendered an entire decade of meticulously crafted global export control legislation fundamentally obsolete in one afternoon. It turns out that Washington's brilliant strategy assumed the physical size of transistors was the only metric that mattered, completely missing the brilliant electrostatic relationship happening beneath the surface. Huawei discovered that perfectly tuning the electrostatic relationship between the gate and the channel suppresses wasted power brilliantly, squeezing dramatically more performance from the exact same sized physical transistor. This specific electrostatic optimization alone delivers switching efficiencies matching 5 nanometer nodes, while entirely relying on older, domestically available 7 nanometer manufacturing equipment that the West happily ignored. This is particularly humiliating when you realize they had already secretly shipped 381 distinct commercial chip designs using these advanced principles long before anyone publicly noticed anything. The iceberg was already fully formed beneath the waterline. While everyone obsessed over the lack of extreme ultraviolet tools, Chinese engineers were quietly validating this entirely new architectural framework. Of course, the absolute biggest headache for this vertically stacked marvel is simply managing the chaotic heat generated by billions of logic switches firing furiously within a microscopic sandwich. Unlike passive memory stacks, active logic layers produce blistering temperatures that can literally melt a smartphone if not perfectly mitigated, making thermal dissipation their single most critical upcoming challenge. Data centers can afford ridiculously massive liquid cooling infrastructure, but a pocket-sized mobile phone cannot. So resolving this spicy thermal puzzle remains the key to their entire futuristic roadmap. Despite these hurdles, the sheer audacity of targeting 1.4 nanometer equivalent densities by the year 2031 proves they are absolutely not planning to slow down anytime. Meanwhile, Western giants are aggressively filing defensive patents in the exact same technological territory, essentially admitting this new timing-based paradigm as a legitimate existential threat to their traditional dominance. Samsung and Intel quickly pivoted their roadmaps to include electrostatic efficiency metrics, proving that nobody can afford to ignore a 40% leap in data center power consumption efficiency. Taiwanese manufacturing titans drastically increased their research budgets to address these new electrostatic paradigms, scrambling to defend their market share against an architectural breakthrough they utterly failed to anticipate. The entire global artificial intelligence market, potentially worth $500 billion soon, heavily depends on precisely this kind of power efficiency to keep massive cloud infrastructure from overheating. And naturally, a meaningful reduction in electrical leakage compounded across thousands of servers represents billions of dollars in operational savings, dwarfing the initial manufacturing costs of these revolutionary processors. Perhaps the most shocking revelation is the existence of an operational prototype extreme ultraviolet machine sitting inside a highly classified Shenzhen laboratory, complete with salvaged European optics and lasers. While it hasn't mass-produced chips yet, successfully generating the notoriously difficult 13.5 nanometer wavelength light shatters the comforting illusion that China was permanently locked out of lithography. They reportedly gathered former European engineers and cobbled together secondary market parts, operating in absolute secrecy to reconstruct the most complex piece of manufacturing machinery on the entire planet. The ultimate realization here is that the global semiconductor chokehold was built on a dangerously fragile premise. Controlling one specific machine does not magically halt the progress of physics. American policymakers spectacularly shot themselves in the foot, practically forcing their biggest rival to build a completely independent, hyper-advanced technology stack that no longer relies on Western intellectual property. If you constantly threaten to remotely brick expensive manufacturing equipment sold to foreign countries, don't act surprised when they urgently decide to stop buying your hardware and innovate locally. By weaponizing global technology supply chains, the West accidentally incentivized the largest manufacturing economy to entirely reinvent the fundamental architecture of modern computing from absolute basic first principles today. Now, cloud providers globally are eyeing these hyper-efficient inference processors, realizing that avoiding the exorbitant licensing fees of Western monopolies might actually be the smartest financial decision available today. This isn't merely about surviving sanctions. It is a fundamental shift in how humanity builds computers, proving that the flat circuit board era is finally reaching its messy conclusion. The traditional electronic design automation software industry must completely rewrite its tools, as current programs literally cannot comprehend how to route signals intelligently across a three-dimensional silicon layer cake. Without these critical new software kits, designers cannot properly exploit logic folding, leaving a temporary but massive gap between what is physically possible and what can be commercially scaled. Yet, Huawei's aggressive development timeline shows they are tackling these software limitations internally, aiming to provide a comprehensive reference point for their rapidly expanding domestic tech manufacturing ecosystem soon. The sheer talent pipeline driving this effort is staggering, with major Chinese universities collaborating deeply on sub-nanometer quantum mechanical charge behavior to bypass physical gates originally deemed completely insurmountable. This relentless academic and corporate synergy produced an architecture that dramatically minimizes power leakage at rest, allowing massive data centers to run substantially cooler under continuously heavy computational workloads. Field tests of these processors running actual artificial intelligence models showed remarkable operational stability, proving these are not just carefully selected laboratory prototypes but highly robust commercial silicon products. For the Global South, a new semiconductor supply chain that doesn't rely entirely on a single politically sensitive island offers a rather tempting layer of desperately needed geopolitical resilience. As global power dynamics shift, nations lacking access to advanced American chips might eagerly adopt this new Chinese ecosystem, fundamentally fracturing the unified technological landscape we once took granted. Instead of a triumphant victory for export controls, we might simply be watching the messy birth of a dual-track global computing standard, splitting the digital world straight down the middle. Washington essentially built an incredibly elaborate geopolitical dam, completely failing to anticipate that the targeted river would simply discover an entirely different valley to flow through with terrifying speed. The next big question isn't whether this alternative path works, but whether it ultimately becomes the dominant global standard for scaling processing power once geometric shrinking inevitably goes bankrupt. Because eventually, silicon atoms reach their physical limits, and you simply cannot construct a functioning electronic switch smaller than the fundamental atomic building blocks of the universe itself anymore. When that inevitable physical wall is reached, the entire semiconductor industry will likely pivot towards this exact three-dimensional stacking methodology, ironically following the trail blazed under extreme economic duress. It is remarkably poetic that the most punishing technological embargo in modern history might have accidentally crowned a new king of global hardware engineering far ahead of normal schedule. With 5 GHz speeds firmly on the horizon, this folded logic paradigm could effortlessly match whatever magical nanometer sizes the West attempts to market over the next challenging decade. Naturally, skepticism remains regarding their ability to seamlessly scale this architecture, but betting against a nation that treats semiconductor independence like a literal matter of national survival seems incredibly foolish. The real tragedy for American tech giants is watching their absolute monopoly slowly evaporate, precisely because politicians decided to weaponize the very tools that maintained their global technological supremacy. History will likely remember this as the moment the tech world folded in on itself, rendering decades of planar chip design completely obsolete and humiliating the world's most powerful strategists. So, as the global technology race radically evolves, one thing is abundantly clear: the old rules are dead, and the future belongs to whoever dares to build upwards first.
If you find this video interesting, push like and subscribe buttons. Take care.